Hello, my name is Evelyn Ramirez. I'm in General Physics 1. My teammates are Angel Macario, Abigail Macier, Clarissa Cerros, and this is our lab report number 5. So for the objective of today's lab, we will be measuring the acceleration of the cart using an inclined plane. We will then compare the acceleration to our theoretical acceleration. For the procedure, we began by gathering metallic slabs to tilt the air track. We then measured the slabs in order to find the sine of the angle of the track. After we put the slabs under the air track, we made sure to only put the cart halfway in order to see if it will go up or down. We then turned on the sensor and calibrated them to make sure that the track runs smoothly. We also made sure to add all slabs after collecting the acceleration using 1, then 2, and at the end we added all 3 slabs at the same time. After noticing that the cart went down the air track, we measured the acceleration and compared it to our theoretical acceleration. We make sure to collect our acceleration using the position versus time graph and capstone, as well as that we use the velocity versus time graph to calculate both acceleration and the percent error. So the equations used for today's lab, we use sin times angle equals opposite over hypotenuse, as well as that we used XA equals G sin times angle. For this equation, G equals 9.81 miles per second squared.
These are our Lab 5 results. First, we have to calculate our theoretical acceleration. In order to do so, we need to multiply gravity times the sine. Here we know that gravity is 9.81 meters per second, and in order to find the sine, we just need to put the opposite over the hypotenuse, which also equals distance over 1 meter. So here we have our hypotenuse, which is 1 meter, and then our distance is 0.025 meters. Once we do the math, we get that our theoretical acceleration is 0.25 meters per second squared. This is the table 1, and just like I said, our opposite is 0.025 meters, our hypotenuse is 1 meter, our sine is 0.25 meters, and our acceleration ended up being 0.25 meters per second squared. This is our first acceleration, which was low mass with the same incline as acceleration 2. In order to find acceleration, we need final velocity minus initial velocity over final time minus initial time. For velocity 1, we have 0.60 meters per second at 0.800 seconds, and velocity 2, which is 0.58 meters per second at 3 seconds. Once we did the math, we got that our acceleration 1 equals 0.19 meters per second squared. And then we can calculate our percent error using our theoretical value and our experimental value, which in this case, our theoretical value is 0.25, since it was our theoretical acceleration, minus the experimental, which is 0.19 meters per second squared, and we got a total of 24% error. And this is the graph we have for our acceleration one. And here you can see where we got our initial velocity and final velocity. Then we have our acceleration 2, which is the higher mass, but the same incline. And just like we did last time, we found acceleration using this equation and the percent error using this equation. For this one, we have velocity 1 is at 0.11 meters per second at 0.75 seconds, and velocity 2 is at 0.61 meters per second at 2.9 seconds, which gave us an acceleration of 0.23 meters per second and a percent error of 8%. And this is the graph we created. And here you can see again the points plotted to where we have our initial and our final velocity. Last, we did the acceleration 3, which was high mass and a larger incline. Here we use the same equations as before. Our initial velocity is 0.17 meters per second at 0.65 seconds, and our final velocity is 0.66 meters per second at 2.5 seconds, which gave us an acceleration of 0.26 meters per second squared and a percent error of 4%. And this is the graph we created, and again, like I just said, you can see the points plotted for our initial and final velocity. And last, I have the questions to answer, which were, which experimental acceleration had the most significant percent error? And the answer that we gave is the experimental acceleration that had the most significant percent error was the high mass, high tilt experiment. And which acceleration had the most unexpected value? And the answer we gave was the acceleration with the most unexpected value was the low mass, because it gave us a much larger percent error. And this is it for our lab results. Thank you.
One of the main challenges that we had during the lab was the calibration. It took us a few tries to get the equipment to read the correct values. Sometimes it wasn't matching what we expected, so we had to keep adjusting until the measurements were accurate. Another challenge we faced was finding the perfect balance of the base on the slide. At first, the slide was slightly tilted, which made the car move in the zone. We had to keep adjusting the base until we found the right balance where the car stayed still when it was supposed to. Those were the two main challenges that we had. It took us the most time to solve. Once we fixed them, the rest went smoothly. The mathematical equations were unfamiliar to us, and it was kind of hard for us to get all the calculations correct.